Good morning and hello everyone. Chapter 2 Mathematics for Cryptography. This would be our part 1 and we will talk about modular arithmetic, congruences, and in the next session we will talk about matrices. My name is Kurdo Jaza Mahmoud and I am Haiwan International University's lecturer. Now this chapter 2 objective would be first to review integer arithmetics, then concentrating on divisibility and finding the greatest common divisor using Euclidean algorithm. Then our second objective would be to understand how the extended Euclidean algorithm works, first of all, and then we will use it to find the multiplicative inverses. Third one would be to emphasize the importance of a modular arithmetic and the modular operator because they are extensively used in cryptography. Now, first of all, if we talked about integer arithmetic, in integer arithmetic, we use a set and a few operations. You are familiar with these sets and the corresponding operations, but they are reviewed here to create the background for the modular arithmetics. Now, if we talked about set of integers, the set of integers denoted by z contains all integral numbers with no fractions, from negative infinity to positive infinity, as is shown in figure 2.1. By another meaning, when we say integer numbers, we mean the whole numbers, not any number with fractions. So it will start from 0 to plus infinity, then from 0 downwards, it will be to minus infinity. Now, binary operations. In cryptography, we are interested in three binary operations applied to the set of integers. A binary operation takes two inputs and creates one output, as it is in the normal mathematics. The difference would be in here that we will not use divide, because it will give us the fractions and we will not need any fraction. And we will have our own way to deal with the division. And the binary operation that we are using would be addition, subtraction, and multiplication operations. Now, for integer division, we know what is the multiplication, addition, and subtraction. However, the integer division would be the special case that we will have. Now, in integer arithmetics, we divide a by n. We can get q and r. The relationship between these four integers can be shown as a equal to q multiplied by n plus r. Now, the r would be the remainder, and believe it or not, the cryptography is nearly all about the remainder or the plus r. Now, assume that the a is 255 and n is equal to 11. We can find q is equal to 23 and r equal to 2 using the division algorithm. So now keep it in mind that only a and n is provided for us. Now we will uh, divide 255 by 11. At the first round in here, we will have 225 and then we will have 2. Now 2 multiplied by 11, we will have 22, 3 is remaining. We will bring down the 5 and we will have 35. Now 3 multiplied by 11, we will have 33 and the remainder is 2. Now this remainder is 2 and the division is 255, divisor is 11, and quotient is the 23. Basically, we will have the division algorithm for integers expressed in this way. And why we will express it in this way, this expression will make sure that our division will always have positive numbers or even with negative number, however with no fraction. The fraction is the thing that we will not deal with it. Now we have some facts. Fact 1 would be the integer 1 has only one divisor and it is itself. 1 will be divided by 1 will equal to 1. That's the basic fact of mathematics. And any positive numbers has at least two divisors. From 0 to plus infinity, we will have two positive integer at least. The first one would be 1. So for example, we have 260. It will divide it by 1, what will equal to 260, and 260 divided by 260, it will equal to 1. But it can have more. Yeah, that's correct. We may have more. Now we have divisors of 140. The common divisors for two integers, we will find the common divisors for 140 and divisors for 12. Now each one has its own set. However, in 1, 2, 4, they are common. By another meaning, if we divided 140 by 1, by 2, by 4, we will have a whole number with no fraction. Same for for 12. If we divided 12 by 2, it would be 6. Divided 12 over 4 would be 3, and 12 divided by 1 would be 12. Now, we will call this set, as it is shown in here, as the common divisors for two numbers. Now we have a note, and it says the greatest common divisors of two positive integers is the largest integer that can divide both integers. What do I mean by this? In here, the GCD, greatest common divisor between 114 and 12 would be 4. Why? Because in this set, the number 4 is the greatest one that both and these both integers can be divided over 4. Now we have another note, Euclidean algorithm. The fact one would be the GCD of a comma 0 would be a, or the greatest common divisor would be divisor for uh, let's say 10 and 0, it would be 10, and the GCD for a and b will be equal to GCD of b and r, where r is the remainder of dividing a by b. Now in this case, let's say that 10 and 3, the GCD would be 3 and 1. Why? Because if we divided 10 by 3, uh, it would be we will have a remainder of 1. We will have 3 with some fraction. However, we will not take the fraction and we will say plus 1. Now, Euclidean algorithm. It will work. We will take a look at the slides now. Now the node, when GCD A and B is equal to 1, we say that A and B are relatively prime. So take care of relatively prime when they are equal to 1. We will use it in the other parts of the slides. Now let's have the example in here. Find the greatest common divisor, and it would be GCD for these two large numbers. Well, when the numbers are small, we kind of can just use the division. When, for example, when it is 140 or let's say 100, something like that, you can just do it by calculation. However, when the numbers are big, we will use another technique. And in order to explain that technique, it is already explained in here. However, we will try the slides that I've been prepared for you. Now, also, we will provide you with this slide. The first one would be the GCD for 200, 2740, 70, 60. Well, as we explained, that GCD means the biggest number that divide both uh, 20, 70, 40 and 70, 60. Instead of guessing the factors, we divide and take the remainder, repeat until the remainder is 0. Now let's take a look. First of all, we will make sure to divide 2740 by 7060. And in this case, we will have the number 1. We will not finish, or we will not stop until we get 0. Now this one is Q, and it is a reminder. Now uh, as we get this Q, we will also have the reminder of 180. So it has been expressed in this way. 2740 is equal to 1 multiplied by 7060 plus 980. Now, these 980 would be our reminder for this case. Now, we will take the two largest number in here. It would be 7060 and 980. We will take it. We will divide it. We see we have 1 with a fraction. It means that it will not be 0. So we will just neglect it. We will use it this way when 7060 is equal to 1 multiplied by 900 plus uh, 780, 780. Now we will take these two numbers and we will repeat this process. We will divide it. Once we get 0, we will stop. However, now it is 1. And we will see that 980 is equal to 1 multiplied by 780 plus 200. Now we will take 780 was 200. Step 4, as we said, we took it, we put the biggest number in the other side of the uh, this equal sign, then we have the other number. We will multiply it by 3. The, 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 the rule lesson here would be to make sure that this side will be equal to this side. However, the first rule would be as we get 200 and these two, as we take these two numbers, the biggest number which is in here usually would be in this side, and then would be used. It is the must. Now we used it and we multiplied by 3. Why? Because we want to make sure that we will find the biggest number to multiply by here. So we will make sure that this one would be the smallest and we will reach the end of our process as soon as possible. Now we reached it here, and now we will take 200 and 180. Once we take this, we will get plus 20. So 180 and plus 20. We will take these two. And now if we divided 180 divided by 20, we will get 9 with a remainder of 0. We will get a whole number with no reminder. At this time, we know that we reached our destination. Why? Because there is no reminder. Once we got no 0 reminder, we will stop at there. So now if we divide it this way, it would be 9 multiplied by 20, we'll get 180 and with a 0 reminder. So we will stop in here and we say that 20 would be the GCD for these two big numbers. So 2740 and a 7060 would be 20. This would be our final result. Now we have a special case. We say that the GCD of A and B, if it is equal to 1, we will call it relatively prime, which it means that they share no common divisor except 1. So they cannot divide it by any number except 1. So let's say that this is 1000, this is 800. These two, for example, this is not a very true one. However, these two will not be divided by any number except 1. Each one would be divided only by 1. Now, this is extremely important in cryptography because an RSA relies on this, relies on relatively prime, or by another meaning, the numbers should not be divided by any other number. Now, we will come also to this. This is another example for GCD. Step 1 is 65 divided by 25 equal to 2. And the remainder is 15. How did we get this remainder? We get it in here because we said that 65 is equal to 2 multiplied by 25, which would be 15 plus 50 and plus 15 would be 65. Step 2, we will take 25 with 15. Now, if we divide it, we will have a reminder. So we will go on. We say that 25 is equal to 1 multiplied by 15 plus 10. Now we'll take the 15 plus 10. Now we have 15 divided by 10. We will have a reminder, so we will go on. We have 15 equal to 1 multiplied by 10 plus 5. Now 10 and 5, we will reach our destination. If we divide it by 10 by 5, it would be, the remainder would be 0. Now we can say that GCD 25, 65 would be 5. Why? Because it will give us the 0 reminder. So now the GCD of the 25, 65 is 5, or as it is shown in here. So by using these 4 steps, we got to the end of our explanation. Now we will go on and talk about another topic, which we did also this one. However, there's a small problem with here 60, and here says 60, and here says 65. However, in here it is again 60. So we will neglect this one. We will go with 25, 60. However, there's no problem still if it is 5. Now, the extended Euclidean algorithm. We would say that the given two integers a and b, we often need to find other two integers s and t, such as that if the we got s multiplied by a plus t multiplied by b, it would be equal to GCD a and b. And the extended Euclidean can calculate the GCD of a and b, and at the same time calculate the value of s and t. So the extended Euclidean, we can use it to calculate GCD, and also we can calculate it to find the T and S. How? We will now explain it. It would be this process. We will make sure that the A will be equal to R1 and the B would be R2. And the result would be R. Now the R2 will become R1 and the R will become R2, and then they will get another result, which it will be R. And we will do this process until we get 0. As we get the 0, our result would be R1. Or by 0, we mean we will have no R or no reminder. And in this case, for finding the S, it would be, first of all, S1 would be 1 and S2 would be 0. And in the vice versa, T1 would be 0. S in here is 1, T would be 0. If S2 is 0, the T2 would be 1. And so on, same process as in here. Now S2 would become S1, S would become S2, and we will have S until we get the result. Now S2 would be S1 and S would be S2, and in here S is equal to S1. So this would be our S, and this would be our T, and this would be our R, or the result of the GCD. Now we will explain what does it mean. First of all, we have this way. We have the GCD of 25, 65 will equal to 5. However, what we are using, we will use a simple technique, and we will also use this technique. First of all, we mean by what do I mean by this? We say that the 5, which was the GCD, the greatest common divisor for 25 and 65, is equal to 25 and 65. However, the 25 will be multiplied by something, and 65 would be multiplied by something. If we add addition these two or plus these two numbers, we will get the 5 again. So we already find the GCD of 25 and 65 is equal to 5. Now we want to make sure that that something would be A, and that other something for the other side of the plus would be b. We will just give it these two variables. Now, from the Euclidean algorithm, we had these. Now, the magic starts from the last equation or from here. Start with the 5. Now we want to make sure that we will get the 5 in this side. We got it. How? Because in here we said that the 15 is equal to 1 multiplied by 10 plus 5. However, if we just change the place of this 15 with this 5, we will also get the same idea. We will say the 5 is equal to 15 minus 10, which would be 5. 5 is equal to 5. It is 100% correct. We just rearranged it. We did nothing. We just made sure that this 15 comes here and this 5 comes to the other side. Now in the step 2, we have something. We reached here. We need to make sure that this number with this number will be replaced. How? We will talk about it. Now step 2, replace the 10. Now we'd say that the 25 is equal to 15 plus 10. Now if we rearranged it, would be 10 is equal to 25 minus 15. We will use D3. However, we will make sure that this 10 will be in this side. Once we made it this way, we say 25 minus 15 again is substitute into the equation or replace it with the place of the equation. Now we had this number. We had this already. 5 is equal to 15 minus 10. Now this 10 we can change it with this because 10 is equal to this, and we will change it with this. Now we will have what? We will have 15 minus 25 minus this. We just change this 10 into this. Now if we simplify it, we will have a 5, 15 minus 25 plus 15, or we will have 5 is equal to 2 multiplied by 15 minus 25. 2 multiplied by 15 would be 30 minus 25 is equal to 5, and then 5 with this side will be 5 again. It is the same. Now we remove the 10. Okay, we removed the 10. Which 10? This 10. We removed it. Now we'll repeat the process and we'll replace the 15. We replace the 10 and we will replace the 15 also. From the first equation, 65 is equal to 2 multiplied by 25 plus 15. Now we will rearrange it, and it would be 15 would be equal to 65 minus 15, and 65 minus 50 would be 15. Now we will substitute again. We had this from before, from this step. Okay, we have that. We will take it here, and this 25 or this 15, we will make sure to rearrange it. Now this 15, we will make it this 2 multiplied by 65 minus 2 multiplied by 25 and minus 25. We just replace the 15. Now we will simplify slowly. 5 is equal to 265 minus 4. 4 multiplied by 25 minus 25. We will have 5. In this side we will have 265, and in this side, side we will have 5 multiplied by 25. Now we will have 5 is equal to minus 5 multiplied by 25 plus 2 multiplied by 65. We said that we want to find those somethings, or the A and B, whatever you call it. Now we found this, and we say that if we multiply minus 5 with 25, it would be minus 125. And in this side, we say that 265, if we multiply by this, we will get 113, and if we minus these two, we will get the 5, and this would be our final answer. Now, in one line summary,
we say that the normal Euclidean, we will use it to find GCD. However, the extended version or extended Euclidean will find how to build the GCD using the numbers. So now also we will explain this extended GCD in this style. Now we have 168, we have 228, and this is the solution, or this is the example that has been given to us. 168 b is equal to 28, and find the GCD of a and b. First we need to find the GCD and the value of s and t. Which value that we are looking for? We are looking for this s and this t. However, we have a and b, and we will have also the GCD of a and b. Now we know that the GCD is of 100, 161 and 28 is 7. Now what we will take would be, first we will rename them as in here. Now from here we say that 61 is R1, 28 is R2, and the remainder of these two would be 21. How? We will now take a look at it. Now, in order to use the extended GCD, what we need to do is the R. Now, this 161 is R1, this is R2. Now, the S would be 1, 0, and this would be S1, T1, S2, R2. Now, why we say this? These two at the first round are fixed, because if we use the S in here, we say 161 is equal to 161 multiplied by 1. This S, we will put it in here, and it will become this, and the 0 would be this, and now this is true. Also same for this, and now we get this. Anytime you want to use this technique, first of all, you need to calculate the Q. How to get the Q? We will have R1 divided by R2, or 161 divided by 28, and we will get a number, of course, 5.75. This is the number. However, we will neglect the fraction because it is in these type of brackets, and this means that we will only take the whole number. Now we have a Q of 5. You may ask me, why do you need Q? I will ask you in a few seconds. Now we got the Q. We got the Q because we will need for calculating new R, new S, new T. We already have R1 and R2. However, for extended GCD, we will need another R. Now, however, to make sure that you will calculate the new R, that R would be equal to R1 minus Q multiplied by R2. Now we know that this R1 is 161 and R2 is 28. However, at this Q, we got it this way. This is why we need the Q. Now we would say that 161, which is the R1 in here, minus 5 multiplied by 28 would be equal to 168 and minus 140, and it will be equal to 21. You might ask me, well, what is this minus? It is this 5. However, it had the minus in here, so that minus it is from there. Also, you can just neglect it and make it this way. For example, it would be the same. Now 5 multiplied by 28 would be 140, and we have 160, and 161 minus 140, it would be 21. Now we got a new R. We will need an S, a new S also, because we have S, S1, S2, we will need an S. Now the S would be equal to S1 minus Q multiplied by S2, just the same with the R. And for the t, same equation. So we will just uh, explain this slide, and for the other side we will not just go as deep as this. Now s would be equal to s1. S1 is this one. Q is this one that we find it in the first place. Now the S2 would be, this is the S2. We will say 1, S1, Q, and S2. We will get 1. Now for the T, remember this is T1 and T2. We will get T1 minus Q multiplied by T2 is equal to minus 5. Now verify the sanity, or verify that it is correct. Now if we put the R, S, and T, we will check it. Now we will put the S in here. S is 161, and the T is minus 5. So now 1 multiplied by 161, the S multiplied by 161 is this number, plus minus 5, which is the T multiplied by 28. If we did this, we will get 161, and minus 141 would be the 21, and this 21 would be the R. And because we want to just make sure that it would be this correct, now you see that this 21 and this 21 are the same, so it means that the S and T that we got, now they are correct. Now we will do the same, however we will take the new R's. Now the R2 of the previous slide would be R1, and R2 was 28. Now it is R1, and R will be R2, and they are 21. You might ask me why this happens, because in here it says that, just let me erase this. Okay, and we in here we said that the R1 is A and R2 is B, and they will get R. However, this B would be R1 and the R would be R2, and same for the S. S, we said that the 1 and 0, then the 0 or the S2 would be S1, and the S would be S2, and they will get an S. And same for the T. Now this is how we said that R2 is equal to R1, or S2 is equal to S1. Now see in here, S2 is equal to S1. This is how we got it. And then the S2, S1, S is equal to S2, and Y, because again S would be S2, and T2 would be T1, T would be T2. Now we will again redo it. Now we have 28, we have 21. Now 28 and 21, we put it in here. Now this is R1, R2, S1, S2, T1, T2. Now we will calculate again. For the Q, we said that we will divide these two, and the remainder, we will take the whole number. We will not dictate this small remainder. We will just take the one. Now our Q is 1. We will say R is equal to R1 minus Q multiplied by R2. We will get, now for the R we get 7. For the S we get minus 1. For the T we got 6. And if we checked and verified this one, we will put it in here. We will say minus 1 multiplied by 161 plus 6 multiplied by 28. We will get the remainder of 7. And this 7 was this one, as we checked it before. Now you see, anytime we get the remainder of 0 when we calculate the R, that would be our point of stop, and the previous step would be our S and T, because after all we are looking for S and T. Now in this step we will calculate the Q. We say that the Q is 21 and 7. Why? Because this is 21 and the reminder. We will take the 21 and reminder. Even for the other previous one, we did the same. In here, same. Now we take the reminder with the B. We took B 28 with the reminder. Now this is 28 with the reminder. And in here we will take the 21 and the reminder. Now 21 divided by 7 would be 3 with 0 reminder. So it means that we reached our destination and we will solve. Now the GCD, or let's say small GCD, is equal to 7. We found this one. And we say that the S and T, S is -1, T is 6. You might ask, well, where is this 2? Now S is equal to -1, S is equal to -1. Now the T is 6, and the other slide says T is 6. This is how we got it. So once we reach 0, we will check the previous step and we will take those T and S. And now we had this, we have S multiplied by a T, addition to T multiplied by B will be equal to the GCD of A and B. We know that the GCD of A and B is 7. So let's take -1 and 6 to make sure that it will be 7. -1 multiplied by 161 would be -161. And 6 multiplied by 28 would be plus 168. If we just subtract these two, we will get 7. So yes, the S, which is -1, and the T, which is 6, if we put it in here, we will get the GCD number of A and B. So that's how we explain it. Now the extended being explained, the extended Euclidean algorithm will be explained it in the both way. I mean, in this way, in this way, and in the other simple way. Now also we have these. We said that in this case it would be in A and 0 GCD, we will have the A would be equal to A. And this is one of the rules that we wrote it before. And the S is 1, the T is 0. Now again, it is the same 0 and 45, and it would be 45 and the 0 and 1. Uh, just take a look at here. If it is 17 and 0, it would be 17. Same as here, 0 and 45, it would be 45. However, the changes, S would be 1, S would be 0. Why? Because the 0 being changed, so this one will be also changed. And the T is 0, T would be 1. So it would be vice versa. If the place of the 0 change, if it is in here, the S is 0. If the 0 is in here, the T would be 0, and so on. Now we explain what is modular arithmetics, and we will try to explain it. Now we will have A is equal to Q multiplied by N plus R. Just make sure that you'll remember this. Now we have mode. What we mean by mode, we will explain it. Now if we say 27 is mode 5 is equal to something, how did we find this? It means that we had 27 in this side and we had 5 in this side. We need to make sure that these two would be equal to each other. So now if we made it 5 plus 2, now 5 multiplied by 5 would be 25, plus 2 would be 27, and now 27 is equal to 27. Now this reminder would be the mode. This is how the reminder is find. Now the 36 with mod 12 would be 36 mod 12 multiplied by something plus something. Now if we multiply by 3 we will get 36, so we will put this one 0 and that reminder would be 0, so this one is the 0, and so on, as also is explained in here. Now set of residues. The modulo operation creates a set, which in modular arithmetic is referred to as the set of least residues model n, or Zn. So the least residues model n, also Zn, are the same. You see the Zn will start from 0 to n minus 1. What does it mean? So now for this, it would be, let's say if it's 2, n minus 1 would be 1, so 0 and 1. Now if this is 6, it would be 6. 6 would be 6 minus 1 would be 5, so 0 to 5. 11 would be 11 minus 1 would be 0 to 10. Now the congruences means that these two, if we moded these two numbers by 10, we will get, for example, 0. If we say 2 mod 10 is equal to 0, also the 12 would be 12 mod 10 will be 0. So the congruences mean that these two numbers, they will have the same reminder if we mod it. Now we will also do this one and we will see. Now let's say that 12 is equal to 10 multiplied by 1 plus 2. Now we say that this one is positive 2 or just 2. Let's say that not positive, we say just 2. Now how about 2 mod 10? So we say 2, we have 10, we should multiply it by something and plus it with something. Now how about if we made it minus 1? We'll have, sorry, we will do it again. For the 2, it would not be minus 1, it would be 10 multiplied by 0 plus 2. It was for the negative. We use the minus for the negative ones. Now this would be 0 plus 2 is 2 is equal to 2. Yes, so congruences means that this number with this number, the mode of, if we mode it by 10, we will get the same result. That would be the congruences. Now same for 13 and 23. If we did mod 10, we will get the same result. Now residue classes. A residue class of A or AN is the set of integers congruent of model n. By another word, they are all the congruent of model n. So the A of n, they are all two congruent for n. If it is 0, they are all congruent for 0. If it is 1, they are all congruent to 1, and so on. Now we have comparison of a z and zn using the graph. So we have the z, which is in this between minus and now minus 1 and 2, 1, 0, 1, 2, and then from this in minus 1. However, the z would be in this between. We will see now how. In here, it says that the A is congruent to 2 mod n. Now, we use modular arithmetic in our daily life, just the clock system. However, the modulo is 12, not 10 or any other number. Now we will explain the operations in Zn. Now we say, for example, in here, add 7 to 14 in Z15. This means that add 14 to 7 and mod 15. Now we will have 21 mod 15 and it will be equal to 6. And we say that the 21 would be 15 multiplied by 1 plus 6. 15 plus 6 would be 21, and that's how we got that 6. Same for here, however, this one says subtract 11 from 7, so 11 from 7, so minus 11, 7 mod 13 would be minus 4 mod 13, and it will equal to 9. Now, same for the other one also. Now perform the following operation. The input come from either Z or Zn, no problem. So again, add 70 to 27. Now we will get a 44 for 14. And these two, actually, this is wrong. The solution that has been provided in the textbook, also wrong. Now, in order to do that, we will say 17 plus 27 is equal to mod, or not equal, mod 14. Now this would be 44 mod 14. Now just let me erase it. Now 44 mod 14. Now 44 mod 14 will be 44 14 multiplied by 1 would be 28 by if we did it with a 3, we will get also something like this. So 14, if we did it, I think with this one, so we would say 17 multiplied by 27, it would be 37 44. Now 44 we will put it in this side, and we will use the 14. Now the 14 multiplied by a number plus a number need to be equal to 44. Now if we say the 1 time of 14 would be 14, 2 time would be 28, 3 time would be 42, plus 2 we will get this, so now the remainder is 2, and so on for the others. It is just the same solution in here. Subtract 43 out of 12 and mod 13 and so on. Now we have properties. We will explain the properties in here. Now the first property, now properties. First property is A plus B mod n would be A mod n plus B mod n mod n. And what do we mean by this? Just take a look at, for the subtraction would be same, only here changed. For multiplication would be the same, and only here changed. We will explain the first one and then we will go with the other one. So now let's take a look at here. Now you see this one being written here says that this big number mod 11 is equal to 8, and this big number mod 11 is equal to 9. So it would be like this. Now this is 8, this is 9, and if we multiply if we addition these two, 8 and 9, it would be 17. Mod 11 would be equal to 6. Now, how did we get this big number to be 8? So we will make sure that we will not plus these two and then we will to find their modes. That would be a lot of problem or a lot of headache if we put it this way. Now we have this big number, 1,723,345 and 2 and 24 945. These two big numbers, we will do something with them, so we will make them smaller. So this would be this and this would be this. Well, you may say that how does we calculated this one? It would be a lot. Now I'll say we will find something for this, we will find something for this, that it is the smaller number. Now how did we find this number became 8? Okay, we have this number with this number of mod 11. Now this number we say that it is equal to 8. How? We will first the big number we will divide it by 11. Why? Because the mod is 11. Now if we divide it by this, we will get a number. Okay, however that number we will do this. Instead of a long division, we check this. We will say 11 multiplied by 160 is equal to this. Now we will subtract these two, we will get 8. So now this number mod 11 is this. For the also this one, we will calculate 11 multiplied by 90 uh, 109 1093 with 177 is equal to this number. Now we say that the 177 is a lot. We will try 176. We will get this one. Why? Because you see in here 2124947. Now here's 945. So it is two numbers more than the actual number. So we will try one less, 11 multiplied by this number. So now also we will say 11 multiplied by this, we got the smaller number 936, now 945. So now we got something. Now we will subtract the actual number with this number, which is in here, we will get 9. Now if you divided this number, we will use calculator, say divide by 11, you will get this number 156667. 156667. We will only take this part of it. How about this one? We will say that this number, let's divide it by 11. Divide by 11. We got 193,176. Now you see also 176 in here is correct, so we will take this part and we say this multiplied by 11, we will get 196 as it is in here. So this is how we got this number. We just divided this big number by 11, this big number by 11. They gave us another number. We will again multiply that number with 11 and we will subtract these two numbers, and so now we got this. Now this part became 8 and this part became 9, so now 8 and 9 mod 11 is equal to 6. An example of mode to the power. However, this will only work for mod 3, 6 or 9. Just be aware. Now if I told you what is the mode of this number, 10 to the power of 100 mod 3 is equal to how much? You may try to 10 to the power 100, it will become a very large number, and then it will try to find the mode. Don't do that. Just do this. Say the 10 mod 3 to the power of here, put a power in here. Now 10 mod 3 is equal to 1. Now 1 to the power of 100 or 1 million, it would be 1. So now no need for extracting the power or uh, extracting the 10 to the power of 100. And it would be the same, it's here as explained at 10 mod 9 is equal to 1. And if we say 10 to the power of n is any number, we will just do it like that. We will say 10 mod 9 to the power would be over here, parentheses, it will be equal to 1. Now, these were the properties that we explained it. And this is the 10 to the power of n mod x would be 10 mod x as explained in here. We'll apply the third property of n times. Now, we have been told in arithmetic that the remainder of an integer divided by 3 is the same as the remainder of the sum of its decimal digits. We write an integer in as the sum of digits multiplied by the power of 10. And it was this example that we explained it. However, also we have something else. We could say that 6,000 would be 6 to the power multiplied by 10 to the power 3. It would be 6000 plus 3 to the power of this would be 300, 6,371 multiplied by 1 plus 70 plus 10 to the power of 10 power 1 multiplied by 10 to the power of 0 would be 1. 1 multiplied by 1, 1. Now this is this. Okay, you might say, well, why did we did that? Because I say that in the mode 10. See if I have it in here. Where is it? We can, for the mode of, well, I'll find it now. Okay. For the mode 3, if we addition 6, 3, 7, 1, and mode 3, we will get uh, the same. Now, this way, 6, uh, 3 and 7 would be 10, and 1, 11, 6, 17. So 17 mode 3 would be equal to a number, and instead of defining this, we will just say 17 mod 3. Now we have inverses. We are working in a modular arithmetic. We often need to find the inverse of a number relative to an operation. We are normally looking for an additive inverse and multiplicative inverse. Okay, so we are looking for these two, additive and multiplicative inverses. An additive inverse would be the relative to an addition operation, and multiplicative inverse relative to a multiplication operation. Now we have some rules. We say a plus b is congruent to 0 mod n. So for additive, it should be 0. We should get 0. For multiplicative, we should get 1. These two numbers should be in your mind. Now we have a note. In modular arithmetic, each integer has an additive inverse. Of course, the sum of an integer and the additive inverse is congruent to 0 modulo n. We should always keep in mind the 0 for additive. Now find all additive inverses pairs in Z10. We will say that for Z10 we have these 5 and 5, 4 and 6, these two, these two, these two, and 0, 0. Why? If we say 2 plus 8 is equal to 10, 3, 7, 10, 5 and 5, 10, 1, 9 and 10, and so on. And if we find the mode, we will say the 0, 0 would be 0 plus 0, because this is the rule, is equal to 0 mod 10, 11. Now for the, let's say the 9 and 9, why we say that it is 0. Now let's take this one in here. Now say 1 plus 9 it would be equal to 10. 10 mod 10 is equal to 0. 2 plus 8 would be 10. 10 mod 10 is equal to 0. And so on. So this is for additive. Now for the multiplicative inverse, we say that A multiplied by B is equal to 1. In modular arithmetic, an n, of course, congruent to 1 mod n. That n could be anything. In modular arithmetic, as an integer may or may not have a multiplicative inverse. When it does, the product of the integer and the multiplicative inverse is congruent to 1 modulo n. So if it has multiplicative inverse, we will get 1. If any other number, we will get, that would be, it means that we have no multiplicative inverses. Now we have multiplicative inverse of 8 in Z10. Now the solution is there's no multiplicative inverse because GCD of 10 and 8 is equal to 2, not 1. So at this time, it means that this gentleman has no multiplicative inverse. No multiplicative inverse. Why? Because the GCD of 10 and 8 is equal to 2, not 1. If it was equal to 1, then yes, we had no problem. Now, this example, find the multiplicative inverse in Z10. Now, it doesn't say 8 in Z10, it says Z10, it would be this, because 1 and 1, 3 and 7, and 9 and 9. It gives us three, these three sets. The numbers 0, 2, 4, 5, and 8 do not have multiplicative inverses, just so you know. Now, we say that the 1 and 1. Why? Because 1 multiplied by 1 would be equal to 1, and 1 mod 10 is 1. 21 mod 10 is 1. 81 mod 10, if we just take this part, we say that 81 mod 10 is 1. And how? Because if we say 81 is equal to 10 multiplied by number 8 plus 1. Now this would be 80, 80, and we have the plus 1. Now 81 equal to, the other one was not clear, is equal to 10 multiplied by 8 would be 80 plus 1. 80 plus 1, 81, 81. Now we have no problem. So that would be the multiplicative inverse of Z10. Now for all multiplicative inverse pairs in Z11, uh, we will say that it is this and that, this, and these two. Because for the multiplicative inverse, if we find the GCD first for 2 and 6, it should be 1. And just you can do it for yourself for checking. Now we have the extended Euclidean algorithm uh, finds the multiplicative inverse of b in Zn, b in Zn, when n and b are given. When this n and this b are given, and the GCD of n and b is equal to 1, because we said the multiplicative inverse, these two numbers that we have, for example, in here, if the 2 and 6, their GCD is not equal to 1 of these two numbers, let's say, that would be a problem. So it means that we have no multiplicative inverse. Now, the multiplicative inverse of b is the value of a t after being mapped to Zn. Now, again, we have the extended Euclidean algorithm to find the multiplicative inverse. Hopefully, you understand it in the first part, and we will take a look at 26 and 11, and hopefully, or this one. Let's take a look. Yes, we have 123. So we will take a look. I will put this one. This one would be the homework for yourself, just so you do it and you understand it. We will do this one. If you remember, we said that for the extended Euclidean, we have R1 and R2, and this would be the R. Then R2 would become R1, and R would be R2. And we will do this until we reach the remainder of 0. So this is the normal GCD. How about the T1 and T2? Now we will find the T. So in here it says the GCD of 120 is 1. And no wonder, if it was not 1, it means that there's no multiplicative inverse. Okay, so now, yes, there is multiplicative inverse, and we will find it. So it says the inverse of 23 is minus 13 or 87. Now, this is the solution. Let's see how it find it. Now, you see, you should be very careful with me. We say the s multiplied by 100 plus t multiplied by 23 is equal to the GCD of these two, which is 1, which we know it is 1. The GCD of these two was 1. So now this number, we need to find the s and the t, so it will be equal to 1. If we multiply s by 100 plus t multiplied by 23, it should be 1. Now we have R1 and R2, S1, S2, T1, T2. Now it means this 100 is equal to 161 multiplied by 1 plus 23 multiplied by this. Sorry, not 161, it would be 100. So now 100 is equal to this one. We just put the s and 0 in here. Now the s is 1. We will put this one in here and this 0 in here. Now we have no problem with the 1 0 0 and 1. However, we will not just say that it is 1 and 0 0 1. We will need to find the other numbers. Now first of all, we again calculate q, and the q will take the whole number. Now the r would be r1 minus q multiplied by r2. Now we say the r1, or the r will be equal to what? To r1. R1 is 100 minus 4. This minus took it from the equation. and the 4 is this 4. Now 23, which is the R2, we got 8. Now the R is 8. Now, of course, for the next step, we will take the 8 with 23. However, we will not just rush. We have the S. S is equal to S1 minus Q multiplied by S2 equal to 1 minus 4 multiplied by 0, and we got 1. Now the T is equal to T1. T1 is 0, and we have the Q, which is 4, and we have the T2, which is 1. Now 0, 4, 1. As we explained it, now we have a minus 4. Okay, so now let's check the vanity. We say that if we put this number, it should have no problem. Now S multiplied by 160 would be 1 multiplied by 100. I don't know why 160 should be 100. It is from the other slide. That's why actually. S multiplied by 100 plus T multiplied by 23, we should get the R reminder. Now 4 multiplied by 23 would be 92, with the minus would be minus 92, and 1 multiplied by 100 would be 100, and the reminder is 8. Now we have a reminder and then S and T. Now we will go to the other slide. Now, as we said that we will take this reminder with this one because this is the rule. R or R will become the R2, the R2 will become R1. Now we have R1 on R2, S, T, S1, S2, T1, and T2. Now you see this is S and this is T. 1 and 4. 1 and 4. Now if we calculated this, now we will get the remainder of 7. So we should take the 8 with 7. 8 as 7. Now in here we will check when we get the R is equal to 1. Again, we will calculate the R and the S and the T. I explained in the Euclidean algorithm and I explained it in here, so I will not just do it again and again until we get the reminder of 1. That's reminder of 1 is the place that we will stop. Now we will say that the final answer is equal to 3 multiplied by 100 plus minus 13 multiplied by 23, and it would be equal to 1. If we check this one, you will also get the 1, and the inverse 23 mod even of this one would be minus 13 to congruent 87 mod 100, and again the both would be 1. And also you could do 12 and 26. It's quite easy. You just find 26 and 12. 12 multiplied by 224. The remainder would be 2. We will take the 12 and the 2 in here, and we will get 2 and 0 because in here we have the remainder of 0, and the GCD is 2. The inverse does not exist. That's why we will solve in here. We said that GCD of multiplicative inverse should be 1. Now addition and multiplication for Z10, you see that 1 and 1 plus 1 would be 2, 2 with 2 would be 4, and these are tens, 9 with 1, and so on. Then this is the multiplicative. The 1 with 3 would be 3, with 3 with 2 would be 6, and so on. Just the multiplication and addition, just nothing more. Now the different sets. We have Zn, we have Zn and asterisk sets. Now the Z6 is equal to 0 to 5. However, for the multiplicative, we should not have a 0. So we say from 1 to 5. And for the Z7, we have from, because it is addition, we can have 0, no problem. Having for the multiplicative inverse, it should be from the 1 to the 6 and so on. So we need to use Zn when additive inverse, or this part. Let's say this part is Zn for when additive inverse are needed. And we will use set and asterisk when the multiplicative inverse are needed. That's why we have no 0, because at that time 0 uh, will give us 0, and we will need GCD of 1 always. Two more sets. 13 would be starting from 0 to 12. 13 would be 1 to 12, because we say n minus 1 for the set, and 13 would be until 12. That's why we say 12. And this would be the end of this video. I hope you understand it, because this would be the base of our next sessions.